Hi, this is Mike Heumann from G3n4 Research, and this is our webinar on advanced SSDs, PCI Express Gen 4, U.3, and new form factors. Let's give everybody a minute or two to go ahead and join, and we'll get started. Hi, this is Mike Heumann from G3n4 Research. Thank you for joining our webinar. Today, our webinar is on advanced SSDs, PCIe Gen 4, U.3, and new form factors. The webinar is sponsored by Kioxia and Intel. Let me kind of walk through the agenda. So we'll have some extended presentations today. We've got a lot of material to cover, so each vendor will be talking for about 15 minutes. We'll have 3 key questions in that we'll ask the panel, as well as 3 audience surveys. That should take us to the top of the hour, and then we'll do Q&A and wrap up for 10 minutes after that. As normal, everybody who is registered for the webinar will get a link to the video recording of the webinar, as well as a PDF of the slide set. Those should come out sometime on Thursday. Hopefully if there's no Zoom outages or anything like that. But we'll send those out to everybody, and so you'll all get that. So let me introduce the topic a little bit and talk a little bit about our panelists. So from Kioxia, we have Matt Hallberg. Matt's a senior product marketing manager. He's an old hat to these webinars. He's done a few of them before. As is John Michael Hans from Intel. John Michael is a senior strategic planner on the SSD line. And then there's myself, managing partner at G3n4 Research. So, if we talk about SSDs, I mean, one thing, other than death and taxes, it's probably a certainty that SSDs get faster, smaller, and smarter. I mean, if you look at now we're getting PCIe Gen 4 devices, we're from almost 4 gigabytes per second of bandwidth to almost 8 gigabytes per second of bandwidth. And, one can expect the latency will go down significantly by doing that as well. So we'll talk a little bit about that during the discussions. One of the other topics we'll talk a little bit about is U.3. So U.3 is a new standard that basically provides an interface that's common between NVMe SSDs, SAS SATA SSDs, and even hard disk drives. So we'll talk a little bit about that and see what the logic for that is and kind of customer reactions. And then finally, one of the hot topics for several years, the EDSFF, or Enterprise Data Center Small Form Factor. The idea is let's design a form factor specific to SSDs that provides very, very high densities. If you look at them, 32 drives in a one-use server chassis, up to 32 terabytes per drive. So, you can actually talk about the potential for getting a petabyte within a one-use server chassis with EDSFF. So the real question, though, is what happens to applications when we do all these things, right? How much faster do we need? Some people say, hey, guess what? Everything we have is fast enough. But if you talk to people in big data or HPC, they'll tell you it's never fast enough, right? So more speed, more bandwidth, lower latency are very, very important with them. And certainly as DRAM and other non-volatile storages speed up, things like Optane, reducing SSD latency helps keep up with that kind of dimension or that momentum there, and keeps the gap from growing between the two classes of devices. One of the other ones is, how does compatibility across media types simplify application deployment, specifically on U.3? And the question is, do enterprise data centers really mix different flash media in the same server and or even hard disk drives? And then finally, how much smaller and denser do we need? Petabyte sounds really good, right? If you can get the data out fast enough, and then you still have the blast radius issues potentially. So those are some of the topics that we'll talk a little bit about today. And with that, let me go ahead and give it to Matt Hallberg. Matt, I will pass you control, and you should be good to go.
All right. Good morning, everybody. Hopefully everyone can hear me just fine. Thanks for the introduction. Yeah, this is, I think, my 3rd or 4th rodeo with Mike and the G3n4 team. And today we'll be talking about why PCIe Gen 4 for your data center. So to me, the top reasons for going from PCIe Gen 3 to PCIe Gen 4 for your data center are infrastructure, performance, and disaggregation. And I will cover those topics in the slides to come. And of course, the overall question that I care about, since this is what I do as a marketing guy, is how do we fit SSDs into the overall infrastructure of PCIe Gen 4. So first, let's talk about, if I page down, not working, okay. Okay, this is going too fast. Sorry, there's a delay. Up, up, up. This is, sorry guys. What is going on here?
See if I can help you out. What slide do you want to get to there?
Yeah, it's jumping around. Yeah.
Yeah, sorry.
Okay.
I'll just go ahead and move the slides for you.
All
It'll
right.
probably be easier.
Thanks. Let me give up the control then, just so I don't accidentally press something. So, first topic is infrastructure. So, in the PCIe Gen 4 landscape, as well as the PCIe Gen 3 landscape, infrastructure is sort of a big deal. Infrastructure meaning how it all works together, how it relates to you, the end user, can take advantage of NVMe in your systems, and how software stacks, everything else lines up. PCIe Gen 4 chipsets that are on the way are already here, and systems bring more PCIe lanes to the table. When you have more lanes, you have more devices. When you have more devices, your systems can become a lot more versatile. So you can use those lanes to add more storage, more network interface cards, more HBAs, more GPUs, etc. And there are already a bunch of devices today that take advantage of the faster data pipes from PCIe Gen 4. There was a press release a couple weeks ago from NVIDIA on their new A100, which, you know, everyone measures up against the Tesla. The A100 is faster by like 7x on a bunch of the different metrics. So pretty impressive stuff for GPUs taking advantage of PCIe Gen 4. There's also been numerous dual 200 gig Ethernet NICs that have been announced. You know, for some of you who might be running 10 or 20 gig Ethernet NICs, here's a 10 to 20x improvement on getting data out from your box to your network. HBAs, we're seeing a bunch of PCIe Gen 4 HBAs. Usually if your HBA is running at Gen 4, if you have a bunch of Gen 3 drives attached, you're going to basically be getting twice the bandwidth to those drives. And then for the rest of us manufacturers, SSD manufacturers, our PCIe Gen 4 devices can most certainly take advantage of the faster data pipes. You know, as a system admin, with this point, you can pick your preference on your system. Do you want more storage? Do you want more performance? Do you want both? So if, for an example, if you're using a PCIe Gen 4 switch attached to an HBA, you can attach a bunch of PCIe Gen 4 drives at a 1x2 lane configuration and basically get twice the devices that you would have using PCIe Gen 3 and get the same performance. Similarly, you could attach the same amount of Gen 3 drives. Let's say you have 4 drives attached to your switch. You could attach 4 PCIe Gen 4 drives and get twice the performance because the HBA itself is running at PCIe Gen 4. So it's pretty versatile, at least on the storage side, on either adding a lot more capacity for the same performance that you're used to, which is probably super fast, or going for the same amount of devices and twice the bandwidth. Go ahead, next slide, please. On the performance side, so again, the NVIDIA announced the A100, great improvements over the Tesla. I already talked about most of these. The HBAs are going to provide more bandwidth for CPUs and SSDs. On the SSD side, we've been able to demonstrate quite a few areas, faster performance and reduced latency. In fact, we had a great demonstration at Microsoft Ignite show in Orlando last October, where in partnership with Microsoft, Broadcom, and QCT, we were able to demonstrate double the performance on an Azure Stack HCI system that was running at PCIe Gen 4 versus a similarly configured system running at PCIe Gen 3. So, you know, we have seen the performance benefits in the real world, not just on a data sheet, with real world applications. And these are things that you as the end user, as an IT admin, can bring to your customers, which are your employees. Okay, next slide, please. And then the last one is more or less an advanced topic. Disaggregation has been a big word a big dirty word in the IT industry for a long time. It's been a long time vision. Let's, instead of siloing and buying hundreds of general purpose servers, right, where you're basically buying servers that have GPUs, SSDs, NICs, etc., and basically shoehorning your application to a generic server. What you can do now with PCIe Gen 4, because we have all the upgrades on the infrastructure, the NICs, the drives, the chipsets, the HBAs, etc. Now, instead of having silos and having resources that are underutilized on each individual server, you can buy a server that has basically all GPUs and a couple local storage nodes. You could buy a server that has mainly storage. You can buy a server that is more focused on hot storage, or a server that's more focused on warm or cold storage. So the possibilities with PCIe Gen 4 are endless. Disaggregation is a pretty cool thing when you think about it. So now you're buying servers that are basically tailor-made for the applications that you're running inside of your company. So you could have users assigned to go into your compute nodes. If you're doing any work in like AI or ML, you could have users that are now getting a lot more storage out of each server, and then users that use the general purpose servers. But you're really just assigning resources now at a much higher level, where you're not leaving resources on each general purpose server behind. Okay. So why do we need PCIe Gen 4 SSDs? Just a couple examples. So I talked about earlier with disaggregation, you have this thing called a compute node. Essentially, with servers today, and with Teslas and now the A100s, you're able to order servers that have more GPUs. More GPUs require lots of DRAM and very fast local storage to minimize the idle time. Generally, the more you spend on a GPU, the more it costs you in idle time when you're not doing anything with them. So when GPUs are doing checkpoints or things like that, they need to be able to offload the data that's on the GPU as quickly as possible, either to DRAM or from DRAM to the local storage. And then the local storage needs to be able to start pumping the next set of data for the GPUs to start processing on quickly. So having really fast local storage minimizes the idle time. So your GPUs are essentially being in use more frequently and not waiting. So, so for us, we have 2 PCIe Gen 4 drives that fit that bill. We have an enterprise drive CM6 and a data center drive CD6, and these are pretty darn fast. Otherwise, the other uses that you could use for PCIe Gen 4 SSDs are for storage nodes and for general purpose servers. We've demonstrated with other partners, like I talked about the Microsoft demo that we did at Microsoft Ignite, that we're able to really realize the benefits over a Gen 3 system. Our drives, the CM6 and CD6, certain configurations can reach over 1 million IOPS, which to me is a crazy metric. I've been in the industry long enough to remember a long while ago, there were a lot of storage application startups or storage appliance startups that were touting, hey, we've got 1 million IOPS in our box. And it was sort of like the holy grail of performance metrics for a storage system. Now at the individual drive level, these drives are over 1 million IOPS. So it's just eye-popping how far along SSDs and PCI Express have come along in the years, at least since I've been in the industry. And I'm sure there might be some people in the industry who've been here longer for like Bernoulli drives and what's an IOP. So also with PCIe Gen 4, you have improved response times. And we're also, not with PCIe Gen 4, but improvements in the NAND stacking. We're able to get to 30 terabyte 2.5-inch SSDs. And we're actually shipping a 30 terabyte 2.5-inch SSD ourselves, a CM6. Next slide, please. So because I am a marketing guy, I do like to give a slight product pitch because I do get some time to do that. This is our CM6. We announced it in February last year, right before OCP turned into a virtual summit. This is a PCIe Gen 4 SSD featuring the latest NVMe 1.4 specification. It's 2.5 inch, 15 millimeter Z height. It's all baked in-house, our own Kioxia architecture, controller, firmware, and 96-layer flash. And just as a side note, in case you're not familiar with the name Kioxia, we are formerly Toshiba. We made that change in October, and I just wanted to put that out there because some people might remember us as Toshiba. Anyways, the drive itself is a SFFTA 1001 compliant and conformant. That's for U.3, which I'll talk about in a slide or two to come. And it's single port, dual port. So if you're doing regular server applications, single port is great. If you're doing high availability or redundancy and you need dual port, like in a storage or an AFA array, this will fit that application as well. One of the other cool features for us is this is our 6th generation of die failure recovery and double parity protection. What that means is, as the drive gets long in the tooth, essentially, eventually, your NAND's gonna, the dies in your NAND are gonna be, starting to overwear. And if you have a die failure, in general, if you don't have die failure recovery, the drive is gonna go into a read-only mode, and that's it. So for us, if we have up to 2 die failures, the drive will be able to recover from a die failure. You'll still be able to read and write from the drive, albeit at a slightly less performance metric. Lastly, we have different security modes. We're going to be supporting FIPS hopefully by the end of March. And for those who are power conscious, we support 5 different power mode settings from 25 watts all the way down to 9 watts. Next slide, please. Performance numbers are there. We're not going to go over those in general. CD6 is our data center drive. This is a single port drive, so perfect for server applications, perfect for data center applications where you don't need dual port. Also U.3, same security features, same die failure recovery, which I think is one of the only drives in the market for data center that has this die failure recovery. And supports up to 15 terabytes, 1 and 3 drive writes per day, same 5 power mode settings. And then the next slide, please. I want to leave some time for John Michael, so I'm going to breeze through these. So in terms of advanced SSDs, one of the marketing terms you might have heard or might be hearing about soon is U.3. So essentially what that is it's a universal backplane that enables the ability to plug in any SAS, SATA, or NVMe drive, and that includes hard drives. What that does is it allows deployment of really not just an NVMe SSD, but any SSD or drive into a U.3 or universal backplane enabled socket with minimal investment. So for me, my cool application that I think about that is if you're like a small, medium business IT deployment, you're able to buy a system with a universal backplane, and you could do tiered storage within the same system. So you could have a hard drive or a couple hard drives for bulk storage. You could have a SAS or a SATA drive for warm data. And then for NVMe, you could throw NVMe drives into the same server and tier them off. So NVMe is going to be where, let's say, you put your engineering org for all the guys that are doing Docker applications or compiling, et cetera. And SAS SATA for warm data for us marketing folk who are always saving and reading presentations, and then hard drives for what everyone stores on their laptops and forgets about it but backs it up to the network. Lastly, since we are also talking about next form factor slide, please. Lastly, form factors. There are some other form factors that are out there. John Michael will talk about E1S and E1L possibly. There's another one that is in the works called EDSFF 3-inch, and that's designed for server and storage. We actually had a press release about it last month. What this is going to get you inside of a 2U system is a lot more density. So in a 7.5 millimeter thick drive, you could do about 8 terabytes. In a 2X drive, which is 15 millimeter thick, you can go up to 30 terabytes. So in a 1 year or 2 year system, you could put in a ton of drives. So for a 2U system using an E3L, which is a long, you're able to do 44 drives, and if those 44 drives are 30 terabytes, that's 660 terabytes in a single 2U system. Also, some of the cool things about E3S is that there's a lot more performance available. We're able to take advantage of wider PCI lane configurations. There's connectors for 1x4, 1x8, 1x16. You can go up to 40 watts. There's unified connectors. The SFF TA1002 is a multi-protocol agnostic connector, which is also featured in some of the other form factors that my partner at Intel will be talking about. And just there's a better system airflow and cooling that come along with this form factor as well. With that, I believe I'll turn it over to John Michael.
Sounds good. John Michael, let me get you control here and off to the races.
Yeah, I'll see if I have better luck.
You have control now.
Hey, morning, guys. This is John Michael from Intel. So as Mike mentioned, I do our strategic planning for our data center at NVMe. Many of you may know me from some of the industry stuff. I co-chair the NVMe Express marketing work group, so I do lots of stuff with NVMe. And I'm also recently took over as co-chair of the SNIA SSD SIG and the Compute Memory and Storage Initiative. So one of the things that we own is EDSFF and the marketing for all the EDSFF stuff. So if you didn't catch, we did recently just do a big webcast on EDSFF kind of nuts and bolts, and with a lot of the major companies that are investing in EDSFF technologies. So we had Facebook, Microsoft, Lenovo, Dell, HP, Kioxia, and myself on the webcast. So check that out. Yeah, this is trying to change slide here. We'll see if it decides to go very slowly. Okay. I was the product manager for the Intel Ruler SSD on the P4500 series. So actually we did a press release at the Flash Memory Summit in August of 2017. That was pretty exciting. That was a super fun product to work on because I got to talk to a lot of customers about kind of this new first principles approach for designing a brand new form factor for data center SSDs. It was really nice, kind of like NVMe. When I describe EDSFF to people, it's like, with NVMe, you got to kind of remove all the legacy from, basically remove the legacy protocol from that were supporting hard drives, and you start from scratch. And EDSFF was kind of like that for form factors, right? We got to have a first principles approach for creating a form factor. So we have 3 EDSFF SSDs in production today from Intel. So we have the P4500 series, which is our TLC 15.36 terabyte NVMe. And we have that in both the 9.5 and 18 millimeter. I'll talk a little bit about why both those exist here in a sec. And then we have our QLC. So it's our D5 P4326. And this one is optimized for warm storage and capacity optimized storage for the best TCO. So some of the things that we do in this drive are not only use QLC media, which is lower cost, but actually use a lot less DRAM. So basically it's optimized for, 16K random writes or sequential writing to get the maximum endurance. But to doing that, so we reduce the amount of DRAM required on that drive and significantly reduce the cost. And then on the E1.S side, we have a P4511 4 terabytes. And this is the E1.S 5.9 millimeters. This is the very first version of the E1.S that got released. Since then, you'll see we have some new versions in the spec that actually have an enclosure around them, and I'll talk about where those are going to be used for Gen 4 and beyond. But the one that today, 12.5 watts, is actually pretty good for a 4 terabyte drive. And you can see this adds a lot of flexibility. It's about the same size as an M.2, but quite a bit more performance and power. M.2 is only got about 8 watts. So that extra, 4 or so watts completely opens the door for 4 terabytes because 4 terabyte drives did not really work on M.2. You can build them, but the performance does not scale. Checking everybody can still hear me.
You're good.
Okay, yeah, I can't, for some reason Zoom's not showing me the notification where I can mute or anything. So anyways, So E1.L, so this was kind of like when I talked about the first principles approach, when you kind of think about, okay, what should an SSD look like? Well, probably not like a hard drive. So I like the idea of E1.L. You have this really high capacity storage to where you have this PCB and board real estate that actually is significantly increased from U.2. So you can fit a lot more what we call media sites or NAND packages on the board. So you can physically make a higher capacity drive. And then it's designed in tandem with the servers. You can actually physically fit more of them across the front of a 1U because it's literally been designed to fit in a 1U, hence the name E1. The 1 stands for 1U. And the two options for the 9.5 and 9.5 and 18 millimeter give you the two options for scalable performance. So the form factor itself supports up to PCI Express by 8. Most of the SSDs you'll see today are just by 4. The ones that from Intel are PCI Express by 4. But you can allow it to go up to by 8 if you wanted to have a different device type. And there are some server applications that want to use that 18 millimeter design that that has fins that can cool up to 40 watts. And even if your SSD only goes up to 25 watts, you can get better TCO and better airflow by running the fan speed lower. I'm going to talk a lot about PCIe attach and low-cost PCIe attach, what EDSFF is kind of optimized for. And really, it's designed to be a high-volume, low-cost connector that's very high speed, and it's very multidisciplinary. It's used in many different places like OCP NIC, EDSFF, of course, and what we're going to talk about, how that's really going to impact Gen 5 and beyond. The other thing you'll notice, for EDSFF, I mean, literally the heatsink is attached to the drive as part of the enclosure is the carrier. There's no carrier or mounting applications you have to put on the drive. The latch and everything is already included in the drive, so you can just pop it into a server for easy hot plug and serviceability. And you have the LEDs on the front to talk about hot plug and management. So really, it's just been designed to really solve all the data center challenges for dense storage. So when I think about our positioning for E1.L, think big SSDs. When Intel's looking at using this form factor, it's all about building the highest capacity SSDs where we're looking at really dense system configurations. You can see as we move, where we're seeing the most volume today on this drive is with our QLC drives in cloud storage, and they're using it for precisely that, to scale the capacity in a TCO optimized way in cloud storage. So the ones today, if you wanted to go check out, Supermicro has got a box for E1.L, and it fits 32 E1.L's 9.5 millimeter across the front of the 1U. So half petabyte today, 1 petabyte coming soon. And then this is a JBOF version that we went and shipping to some of those cloud vendors I alluded to. This is just the 18 millimeter design. Again, this is really not for, they don't need to really go up to 40 watts. It's still a 25 watt drive, but they're using this just to get a little bit better airflow and cooling. And this is a JBOF, so there's just PCIe switches in here. There's no compute, but this is a nice low cost, high capacity attach for PCI Express storage. Now, I'm going to talk, there's some panel questions about U.3 and SFTA 1001. I'm going to talk about that a little bit later, but just hold this image in your mind when I go to that topic here in a little bit. So this is a Dell PowerEdge R740XD NVMe server. I saw this on the storage review a couple days ago, and I just kind of sparked some interesting conversation. This server supports, I think in one configuration, up to 24 NVMe's, but in this configuration being shown, it supports 12 NVMe SSDs on the front of this 2U server in a U.2 form factor. And the way they do that is through these PCIe extender cards. So my guess would be, I don't know much about the actual system today, but since it's 16 lanes in, 16 out, they can use a retimer. If you were to do something where you had 16 lanes to the host and more lanes to the backplane, you would need something like a PCI Express switch. But this is kind of ridiculous to me, right? So you have these basically 3 PCIe retimer cards, and they're each looks like by 8. And you have these PCIe cables. It looks like Dell is using slim SAS here that go to the backplane. So this is tough, right? When I'll talk about, some of our goals for EDSFF is to kind of solve some of these infrastructure challenges to make PCIe attached, very low cost, scalable, have good signal integrity, doing it with minimal infrastructure investment. And that's some of the goals for some of the EDSFF servers I'm going to show you. But just note this, like if you go to Dell's website right now and click this option, they charge you, I think, like $470 to do this upgrade, which actually, all things considering, is not too bad. But there's a pretty big trade-off here, right? You support 12 NVMe's in the server, you're paying extra. Now, the SAS and SATA attach is not free, and we're going to get into that, where I think there's this common misconception that PCIe infrastructure is more expensive than SAS and SATA, and that's just not true, right? To hook up SAS infrastructure today, you need a RAID card or an HBA, and those aren't free. And Dell and other companies include them in some of the cost of the servers, but you're paying for them, and they take up a slot as well. So hold that image in your head when I get back to the other topic about SAS and SATA compatibility. But so I mentioned today, we have this 4 terabyte E1.S drive, and we actually are seeing a bunch of customers design this in. And you can see it has mounting holes for a carrier, and this was meant to be kind of flexible for different configurations. But going forward, we're actually seeing a lot more interest in the E1.S enclosured version. So there's a 9.5 version and a 15 millimeter version that we're going to be supporting. I'm showing you a picture of a prototype that we showed at OCP that would be potentially at like 15 to 20 watts. So we are going to be doing our PCIe Gen 4 products on this 9.5 and 15 millimeter enclosured versions. And so what do these enclosured versions buy you? Well, they buy you U.2 performance in a smaller form factor for kind of 2, 4, and 8 terabyte class drives, which is a big deal. And I'm going to show you here when the slide changes. But in the recent webcast that we just did with Facebook and Microsoft, and as I mentioned, Dell, HP, and Lenovo, and Kioxia as part of the SNIA webcast on EDSFF. And this is some of the stuff that Facebook showed off also at the OCP Virtual Summit. They have 2 new server designs that are using the E1.S. Facebook's using the E1.S 25 millimeter to get the best thermal airflow, as I mentioned. Kind of bigger heatsink equals less airflow or more power dissipation. And you can see they kind of have some PCIe cables that are going to this modular chassis over here, but this is their mainstream mainstream 2-socket Cooper Lake, which is our Xeon Scalable processor system. And this house is 4 E1.S over on the left here, and then they have 2 OCP NICs. And then they have the Yosemite V3, which they have these little modular cards that support 4 E1.S in each blade as well. So very dense storage for their disaggregated storage boxes. And then Microsoft, so this is their Project Olympus design for E1.S for mainstream compute. And think about, when they did the last Project Olympus, they had used M.2 form factor, and they had M.2s that were down on the PCB, and then they had M.2s in these PCI Express add-in card carrier cards. And so this allows them to have a front serviceable storage with better airflow and cooling. And then this allows them to scale now from those smaller M.2 capacities of like 1 and 2 terabytes up to 4 terabytes. And as we talk about PCIe Gen 4, the extra bandwidth allows you to keep scaling capacity. And so what's important in compute designs is scaling IOPS per terabyte. You don't want to go down in performance as you scale the capacity up. You want to, as you get more cores, you need more performance, and that's where PCIe Gen 4 comes into play. And then their view for the dense storage is the one I showed you. This is the same server as I showed you, that WeWin server. This is actually installed. You can see very exactly the same server. And this is using the 18 millimeter design. This is their idea of dense storage. So looking at EDSFF E1.L for the very high capacity QLC use cases. Sorry, hopefully I didn't freeze here. I'm seeing some weird stuff going on here.
Let me try to move for you, John Michael.
You guys can still hear me? That's good. I'm getting like a spinny beach ball of death here on my Mac, but as long as you guys can still hear me, that's good. I'll keep going. Okay, so this is a cartoon that that the hardware engineers in our data center group drew up for me for E1.S, but just to literally simply illustrate the fact that E1.S was designed for 1U servers. Like, and I have to explain this to people, like, okay, well, what's the value of E1.S versus U.2? Isn't U.2 fine for performance? And, can go up to, as Matt alluded to, like, 30 terabytes plus, what's wrong with U.2? Actually nothing, right? But if you're looking for performance configurations in a 1U server, E1.S is always going to win because it's literally designed for a 1U server. You can see the 9.5 millimeter, you can fit 32 drives across the front of the 1U. And with the 15 millimeter, you can fit 24 drives. And this allows you for low cost PCIe attached. So think back to that picture I showed you with the Dell server and the retimers. Now it's, the jury's out for PCIe Gen 5, whether you'll need retimers or not, but EDSFF has potentially better signal integrity than the SFF8639 connector. So you should be able to even do these type of configurations on Gen 5 without retimers, or in some configurations where there's long trace lengths and cables, you like them. But in this picture, you can see from the CPU, there's little cables here, and they cable out to this backplane, which is very low cost backplane. It's right, it's just a PCB with this surface mount connector. This is called the orthogonal connector, and that's FTA1002. And then you can just easily cable up from the CPUs right over here, or you can have another design that has, kind of the CPU directly routed to the edge connector. It's kind of like, that Microsoft design I showed you in the last page. So, kind of looks similar to that. But think about EDSFF is low cost NVMe attached, right? It's allowing for better scalability in the number of systems as far as capacity per rack unit, number of drives per system. You get more drives and more PCIe bandwidth, so more performance per terabyte, more performance per server. And you know, in U.2, again, you have to fit the drives horizontally in a one use, so it's just not optimal. Okay, so again, you guys can still hear me? It's good.
Yep.
All right, I'm just gonna keep going, even though something bad is happening on my Mac. But okay, so yeah, sorry, the fonts got a little messed up here for some reason, but we actually launched our PCIe Gen 4 drive called the Intel SSD D7 P5500 and P5600 earlier this year, and this is based off our 96-layer 3D NAND, and it's our first PCIe Gen 4 SSD, and this will kind of be the foundation, at least for the next couple years for our PCIe Gen 4 product line, and you'll see this architecture moving to the 144-layer very soon. And we have two versions, right? We have a read intensive and mixed use. This is pretty standard for enterprise today, and most of the cloud customers today are standardized on this one drive write per day type of product, because as you can see, they're very similar. They actually use exactly the same architecture. And I'll talk about one of the features that we have in this drive for dynamic runtime provisioning using NVMe namespaces to be able to actually switch back and forth between this 1 and 3 drive write per day modes if you want. And so one of the reasons people use these mixed use drives are for higher bandwidth mixed workload applications. So think about database, think about caching, stuff that you're going to see a mixed read and write, and you want a higher endurance for because there's going to be more writing. But this architecture does today 1 million IOPS, and what we think is a very efficient architecture. So this is really meant for not only enterprise, but we also use this architecture in cloud storage where you need really efficient performance per watt. And so not only are you need to deliver high performance, but you need to deliver it efficiently. And in some applications where they're not using the max performance of the drive, you need to actually be able to scale the performance per watt down. And we can actually do that through something we call with NVMe power state descriptors or active power states. And I'll talk a little bit about how we do that on this drive. But again, really flexible architecture to deliver really high performance when it's needed and deliver really efficient performance when that is needed as well. NVMe 1.3, we have a handful of some of the new 1.4 features included in this product family. All the standard enterprise stuff like power loss protection, end-to-end data protection, NVMe Express management interface for out-of-band management. And we support today is kind of the mainstream capacities in this form factor. You'll see a broader range of capacities as we move this architecture to QLC and 144 layer, which I can't unfortunately talk about today. But all right, so it's changing slides. That's good. All right, so we talk about this is our new PCIe Gen 4 architecture. This is a 16-channel controller, so it is high performance, but again, it's really power efficient. And it's using our 96-layer 3D NAND. I mentioned we're going to be able to. This architecture is going to be able to support the future as well. And 7 gigabytes a second sequential read. So we're talking about that Gen 4 performance, and there's a question about where is this needed? Well, it's awesome. We already are seeing for mainstream capacity SSDs, the PCIe Gen 4x4 interface is going to be a bottleneck. And as flash gets faster, and as flash channel speeds get faster, and the number of capacity of drives go up, that actually PCIe interface needs to continue to scale to keep up. And we will move to Gen. You'll see moves to Gen 5 and beyond because SSDs are getting really fast. And one of the things, we talk about use cases. Well, the most bandwidth intensive applications that we see today in interest from this drive are, high performance relational database. So think about like Oracle database, Microsoft SQL Server, MySQL, anything that you can get really good, high performance random read bandwidth that can take advantage of PCIe Gen 4 is where we'll see an immediate use. Obviously for AI, for training, ingest, some of the things that you actually need kind of to shuffle around data in the middle stages of AI training. This is really good for that as well. And obviously our Optane SSDs, where you need the ultimate highest performance. And I can't talk about our Gen 4 Optane drives yet, but just go on our Twitter and you can see a sneak peek of some of the stuff that's going on in regards to that. But all I can say is there'll be more information coming soon. And then, for the other Gen 4 uses, there's obviously stuff like, CDN or content streaming or, HPC or any other bandwidth intensive applications. That's just going to be better on Gen 4. So this drive, does 7 gigabytes a second. It's going to read 1 million IOPS. And then one of the things that we do, because this architecture, Intel actually ships this to cloud customers as well as enterprise servers like OEMs. We actually really optimize the firmware for, tail latencies, for quality of service and mixed workloads. And you'll see this generation has 80% lower tail latencies versus the previous gen. I think we're in the kind of like 500 microsecond range for, a random read within a mixed workload, as far as the worst case quality of service. Okay, and then, so advanced feature set, I kind of mentioned, we have done a ton of work on this drive. And so it's kind of funny, we do this work for the cloud customers to reduce tail latencies and improve quality of service through very fancy NAND algorithms that require firmware, controller, and NAND interaction. It's very complicated. And this is one of the things you get as a benefit of designing the controller along with the NAND itself. You get to figure out how these algorithms all work together in tandem but all the work that we've done to improve latency in the cloud has really shined through in a lot of the enterprise server workloads for database, especially in NoSQL databases, like, think about like RocksDB and Aerospike and stuff like that. This architecture scales very well for high performance random reads while there's writes going on. And then we have an all new trim architecture. So one of the things that we saw in these cloud workloads is, they are keeping these drives moving, right? They give these drives into VMs, and they have some customer uses, creates a namespace, and wants to put their VM on this drive, and then the cloud customer may be renting that out to a customer and charging them by the IOPS or by the capacity, and then customer shuts down the VM and the drive goes away. They have to instantly trim all that space to go give all that back to the SSDs, so it optimizes for write amplification and endurance. And this trim architecture operates in a background state machine, so it can do all that basically seamlessly without impacting quality of service or performance, and you still get all the benefits of endurance. So really cool stuff that they built in. And then the other stuff, we actually support multiple namespaces on this drive, I believe up to 128. But the way we use it, the namespaces, is you can do it in a runtime. So you can create a namespace, delete a namespace. And one of the things that we actually do, so if you wanted to get higher endurance, higher mixed workload and random write performance, in runtime, you can actually just delete the namespace and create a smaller namespace, and you can use that as basically a way to over provision the drive. And you can do that, during runtime. So if there's different applications that need different types of performance or endurance, that can be basically done all software automated. And the other thing too that is now all due to the NVMe standard, NVMe has this thing called active power states, which basically allow the drive to report different power states it supports. On the each of the capacities supports 3 different active power states. I believe on the highest capacity of the 7.68 terabyte, I think it's like 15, 20, 25 watts kind of envelope. But you can set these active power states during runtime if there are times where you want to limit the TDP of the drives to be able to fit, say, 24 drives in a 2U server, or if there's other modes where you wanted to run the drives in a lower active power state to get better TCO, you can do all that during active runtime without the need for a reset. And then of course security is a big thing right now. So we have TCG Opal 2.0 for data at rest security, NVMe Sanitize for basically optimized secure erase of the SSD to basically ensure that all the data has been wiped effectively, and it can be measured and demonstrated in a safe way. And then we have the AES 256 hardware encryption on that controller itself to keep the data secure. And so I mentioned a handful of the features of this drive, but I can't go into all these, but really that telemetry, we've done a lot of work on telemetry. Telemetry is a command in NVMe that allows you to dump a telemetry log and then helps vendors basically understand when a drive has failed, or during kind of runtime health monitoring. We have a lot of custom log pages in the Smart to be able to actually have more detailed and robust information than the standard NVMe Smart allows. We also have persistent event log, which is kind of like the black box recorder of all the stuff that happens on the drive. That's one of the new NVMe 1.4 features. All this stuff to really help just people manage the drives more effectively. And then I already kind of talked about the trim and the namespaces for all these new use cases. The namespaces is really interesting because a lot of people want to do, virtualized environments with containers, and a way to do that today, you can use namespaces, and then you can support things like format per namespace. You can support security and OPAL per namespace. You can have locking ranges. If you wanted to, for instance, give cut up a drive into multiple namespaces and give them each separate keys to different tenants. That's all stuff you can do today with the architecture that we have. And again, PCIe Gen 4 helps because you need that extra bandwidth when you have lots of different workloads running to the drive, and you actually increase the total bandwidth. And as you'll see, talk a little bit about going forward and some of the panel questions. I think it's really important as we kind of scale into the future. We're not going to stop at Gen 4. NVMe is not slowing down.
Excellent. Thank you very much, John Michael. So right now we'll go to the panel questions, and for that we'll first start out with our first poll question. And that poll question is, when considering SSDs for your data center, what factors drive your selections? And you can check all the apply. I'm launching the poll right now. We'll give everybody a couple of minutes to do that. And while we do that, let's go ahead and go to the first panel question, which will have Matt answer first, then followed by John Michael. And that is, what are the lead use cases for PCIe Gen 4 SSDs? I know we talked a little bit about that already, but if you had to pick 2 or 3 that you really think from an app standpoint are important, what would you say they are?
I'm on mute, sorry. To me, the lead use cases are, as I said, having fast local storage for GPU nodes. AI and ML are really big today. I mean, they're bingo keywords and marketing terms, but a lot of companies now are looking at the data they have and starting to crunch it to figure out how to, gain more revenue or gain a competitive advantage. So local storage, being able to run databases, being able to run applications that are used in HPC environments are really important.
John Michael, what have you guys seen as the lead use cases? Obviously, you're doing a lot of work with hyperscalers, but beyond that, what other ones have you seen that are important for Gen 4?
Yeah, and I mentioned, the hyperscale use case is really about how do we effectively scale the IOPS per terabyte in cloud compute, and for the mainstream kind of, capacity tiers for cloud service providers that want to offer more VMs, either to customers or for their own scalability, Gen 4 is required there. But like I mentioned, actually where we're seeing the most traction on the drive, I just showed is really traditional database, right? Where one is that's the leading server use case. If you looked, I mean, servers are used for all kinds of stuff, but it's as far as what the actual leading server use case is, it is relational database. So, I mentioned stuff like Oracle, SQL Server, MySQL, those are all accelerated, especially when you're doing, really high TPS for read queries. You can actually get up the bandwidth of the Gen 4 drives. Yeah, and again, I mean, the AI stuff is kind of like, being developed real time. I'm actually, I'm not the expert in that case, but I am told that it helps very much with the ingest phase. So
that makes perfect sense. All right, let's go to the next poll here. The next poll question is, the upcoming U.3 specification will enable U.2 NVMe SSDs, SATA SSDs, and HDDs to fit into the same slot in the server. How important is the ability to interchange media types to your organization? This is a check 1. I will launch that, and we have a couple minutes while we go to the next panel question, and John Michael will start this one. Along those same lines, another technology can replace U.2 is the upcoming U.3 specification. What are the primary drivers for the adoption of U.3 by enterprises, or not drivers for it, if you want to take that approach as well? So John Michael will start with you, and then we'll go to Matt.
Sure. I'll say this, just a preface. Intel's been pretty publicly against this SFTA 1001 specification and I'll describe a few reasons. I literally wrote an entire white paper on why I think this is a horrible idea. So there's many people that listen to me, and I'll go on a mini rant here just to help everybody of why, one, Intel doesn't have a SAS portfolio right now, and we're actually moving all towards NVMe. As you saw, NVMe scales to PCIe Gen 4 to Gen 5.
Hey, John Michael, are you still there? I don't know if we lost you or what. You still hear me, Matt?
I can hear you. Yeah.
Okay.
I didn't
I
do
guess
that.
the tech guys didn't like what he's saying about U.3.
Yeah. Preface Kioxia was not responsible for John Michael going down.
Well, while he tries to get back, why don't we let you try to answer the question? What do you think are the big drivers? And then when John Michael comes back, we'll give him some more time.
Yeah, I mean, so preface for us is we have a pretty wide portfolio of SSDs. I mean, we were Toshiba, so we had hard drives as well. We make SAS, we make SATA, we make NVMe, and for us, it's just we've taken the position of getting flexibility down to IT administrators. Um, so, sorry, just saw ARM comment, but the flexibility is on IT administrators. I mean, we're happy if you guys buy a SAS SSD. We're happy if you buy a SATA SSD. We're happy if you buy a PCIe SSD. Um, we can't assume that everyone's going to just move over to NVMe quickly, as much as we would love that, because we've invested heavily on NVMe on our side, as well as Intel and everybody else. We think flexibility is what people are looking for, and the reality is that hard drives will be around for a very long time. They have a price per gig that just can't be touched with QLC or with anything else. And rather than force customers to move to an all NVMe interface, which certainly has a numerous amount of benefits and advantages in terms of system complexity, et cetera, as John Michael showed you the picture of the mini SAS cable running around. We'd rather embrace what's happening and what's shipping today and be able to give customers the flexibility, or at least give our OEM customers the flexibility to offer drives that can be used in conjunction with other drives into their servers.
Hey, I'm back, guys.
All right.
We're going to give you a chance.
I didn't do that, John Michael. I didn't do that.
That's fine. Matt interrupted my rant with killing my Zoom. That's how angry he was at my So to be honest, this one was really frustrating for me. And I'm just going to go on a mini rant real quick, just to be very clear about Intel's stance on this, because U.2 was designed to be multi-protocol, right? You can support SAS, SATA, and NVMe on U.2 today. You just have to have a different set of cables, and it's one extra mini SAS cable per 4 drives on the backplane. It's like $2. It's we do it on all of our Intel servers today. It's really not that inconvenient. The other thing, the problem with this U.3 thing is that it requires the use of a RAID card if you want, basically all 3 protocols, because you can't flex the PCIe lanes on the CPUs to support SAS or SATA somehow. So basically you have to have the backplane attached to a RAID card, and we don't think attaching high performance Gen 4 SSDs to RAID card is that great of an idea. That people will do it and we're going forward, but you're going to be bottlenecking the performance of the drives. The other problem, and this is my main problem with this whole specification, when they were developing the spec, I actually gave them very clear input that I thought this was a deal breaker, and U.2 drives are not backwards compatible in an SFFTA 1001 slot. Let me state that again. A U.2 drive is not compatible in a slot that supports U.3. Why is that a big deal? Because if you wanted to do a U.3 drive, you basically have to use at least 6 lanes from your SSD controller out to the SFF8639 connector. Basically, it requires this IP called lane switching, which allows the SSD to basically detect whether it's in an old slot or a new slot. We thought this was a very terrible idea because it drives up the cost. So let me just restate that to be super clear, right? They were asking NVMe SSD manufacturers like Intel to increase the cost of our SSDs, increase the capacity and size of the SSD controller to be able to support SAS. I thought this was absolutely insane and terrible idea when the U.2 connector already supports multi-protocol. I won't even go into the market dynamics about hard drives, 2.5-inch hard drives and servers, getting rapidly displaced. 15K drives are already dead. Basically, the SATA SSD killed them. 10Ks are next. I don't think people are going to be really wanting to put 2.5-inch hard drives in a server in 2024 and beyond. So, I'll summarize my rant, but Intel does not support this specification, and our future is really what we talked about with EDSFF and NVMe, and you have to be able to get to NVMe, to be able to scale to the future.
Excellent. Certainly a good, nice, spirited discussion for sure. So our third audience survey question, that is, what is the most important factor for you to consider using new technologies such as EDSF and or U.3 for use in your data center? And this is a check one. I'll launch the poll again on this one. You should see that in your Zoom window, and we'll go to the last panel question. And that was EDSF, and we'll start with Kioxia and then Intel. EDSF was the hot topic in SSDs in early 2019, even going back further than that. What are the hurdles to EDSF's adoption? How long until it replaces U.2? We're asking you guys to get out your crystal ball and tell us what you're seeing and what you're thinking.
Well, I mean, as the product manager for our NVMe SSDs, my personal preference, I would love U.2 to stick around as long as possible. From a manufacturing point of view, it's when you have multiple form factors in the market, it becomes a lot harder to support and do inventory management, et cetera, on. And U.2 has just been a versatile form factor for a long time. There are obvious reasons to move from U.2 to EDSFF. There's performance improvements, et cetera, in Gen 4 and upcoming in Gen 5, where you want to get away from a 25 watt or a 20 watt your maximum power. Of course, not everyone's going to use 20 or 25 watts, but that's one of the main reasons. In terms of when EDSFF will replace the 2.5 inch, crystal ball for me, I think PCIe Gen 5 is when, at least for E3, the E3 form factor, when we see that entering into the marketplace. And for hyperscale, the big three hyperscale guys sort of rule the roost on the form factors as well. If they adopt E1S, for example, then a lot more SSD vendors will adopt E1S. The more SSD vendors adopt the different form factors, the more availability in the market, and the faster the form factors start to take over 2.5 inch form factors in servers and storage, et cetera.
Very good. John Michael, what do you guys see?
Yeah, this is funny. I mean, and you guys can still hear me okay after the reboot?
Yep.
Okay, great. Yep. So, analysts never get this right because, you can't extrapolate run rate business out for a new form factor. As Matt alluded to, if Facebook and Microsoft say today, hey, we're going to transition all of our M.2 to E1.S, that's going to be a very binary transition. They're going to procure and make all the vendors, produce drives that are E1.S, and it's going to shift all the volume. And the cloud is no joke, right? They are, one of those guys I mentioned is 10% of the total flash TAM. And, they actually, drive a large percentage of the market. So it's going to happen a lot faster in cloud. Now, so EDSFF solves a lot of challenges that are accelerated by the move to PCIe Gen 5. So I do, agree with Matt. So for enterprise servers, I think Gen 5 is the time where it'll be very accelerated. So you're solving signal integrity problems. You're solving that low cost PCIe attach problem I just mentioned. You're solving thermal and power scalability problems, and you can get to larger capacity SSDs. But U.2 is still going to be very mainstream through Gen 4 in enterprise servers. Now, in the cloud space, again, I mentioned it's really up for grabs. In a 2U server, U.2 is really still adequate for the near term for PCIe Gen 4, but it's not going to be adequate for Gen 5. And the writing's on the wall where we need to figure out the transition plan, and we're already working through customers there. But in a 1U server, I mentioned, E1.S provides a lot more better value than U.2 because the capacity of drives that some of these cloud guys are using are not these, for TLC are generally kind of the smaller ones, right? Like 2 and 4 terabytes. And in an E1.S, if you can get an E1.S that's the same performance as U.2, but you can scale many more of them across the front of a 1U, or you can use them more strategically without taking up more board real estate, then you actually see a real competitive advantage. And that's the impetus for the cloud guys actually designing them in. And that's kind of the reason why they didn't design U.2 in the first place in some of these cloud guys. Half of them use U.2, the other half use M.2. And I won't get into that holy war of why that is, but it was really all about cost. And E1.S solves the cost problem, but it also solves the thermal power, scalability, and hot plug problems. So it's a very effective solution for scalable cloud storage, especially in a 1U form factor. I'll just be very clear. You know, in a 2U form factor, UDAT2 is still fine, but in a 1U form factor where you're very space constrained, E1.S really shines.
Excellent.
Yeah, and I forgot forgot the topic of the question, which was volume forecasts. You know, Intel's publicly stated that we think about 30 or 40% of the PCIe SSD TAM will be EDSFF by 2024. So that's my stake in the ground.
That's really aggressive.
We'll record that one for posterity. We can all get together 4 years from now and see how you did. So with that, let's go to the Q&A. Our first question is E1S 15 millimeter enclosure. Does that affect density compared to the current E1S?
Yeah, sure does.
I guess, John Michael, that's probably a question best for you.
Yeah, I showed that picture, and it's also in the SNIA webcast. If you go to the SNIA YouTube page, you'll see the webcast we did. I talk a little bit more about it there. But yeah, 15 millimeter, you know, it's a trade-off, right, where you get higher power on the SSD or better thermals, but you can fit slightly fewer of them in the server. And for many customers, that's an okay trade-off. And they see that as a kind of sweet spot for Gen 5 and beyond. So they're designing it in now. And, you know, 15 millimeter, for all intents and purposes, you know, 24 drives across the front of a 1U is quite a bit of flash per server. So that's, I think, more than adequate for many customers.
Excellent. The next question, I'll jump to this one too, because this one's pointed at you as well. How does Intel see the market share between E1S and E1L?
Yeah,
different verticals or different apps, or what do you think there?
Yeah, storage versus compute. So compute drives, which are, you know, drives that are attached to a server where you have a Xeon CPU, and you know, you're doing compute applications. You know, you'll want E1.S because you're looking for scalable performance, scalable IOPS per terabyte, and always the smaller capacity TLC are always going to win on that. For storage use cases, think about like software-defined storage, so like Ceph or ACI or vSAN, or, you know, where cloud storage today, where they're kind of replacing warm storage of hard drives. You know, that's where we see E1.L shine, because it's for high capacity SSDs. So for small capacity SSDs, you don't need the big E1.L board real estate. You don't need that for a 2 terabyte drive, you know, but for a 16 terabyte drive, you really can take advantage of all that extra board space and power and cooling and all that good stuff. So think E1.L, big drives, E1.S, kind of small to mid-range drives.
Very good. Okay, next question. Are any of the storage timelines being impacted by the 17 nanometer delay? Why don't we start with Matt first, and we can jump to John Michael on that one.
It's 7 nanometer delay. I'm gonna let John Michael address that one, because that's a Intel topic.
Intel question.
I'm gonna plead the fifth on that. I don't think there's an answer I can give that would be yeah, I'm gonna plead the fifth.
Understood. No problem. All right, next question. What is SSD tail latency? This is a definitional question.
Yeah, sure. So quality of service is basically latency measured over time. Over a period of time, what percentage of the IOs are going to complete under a certain amount of time. So when somebody says 5 nines QoS, that means 99.999% of the time, the IOs are going to complete under that, you know, 500 microseconds is what I mentioned for our drive. You know, so think about quality of service as your kind of worst case. Now in, you know, database applications, that may actually matter, because when you have multiple drives, multiple systems, you're doing a large query, you know, statistically, if your drive does 99.99%, then, you know, for, you know, every 1,000 IOs, you're going to see one that is delayed. So having a better tail latency requires quite complicated firmware algorithms and, you know, the operations of like suspending program and erases in flight. But basically think about for cloud storage workloads, especially when they scale to tens of thousands of nodes and they're having these distributed graph databases and all kinds of really complicated queries, you know, you want to have an IO, you know, quality of service that's very consistent. And basically, so when you say tail latency, that's just saying like 5 nines, 6 nines, or 7 nines quality of service.
So in a sense, the bigger your problem that you're working on, the more likely that an outlier tail latency is going to bite you and cause you problems.
Yeah, or, you know, to say if you're running one database on one server, as long as the IOs 99.99% of the time respond at a certain time, that's probably fine. But if you're running 1,000 nodes and each one has 24 drives, then 4 nines is not going to cut it. You actually need a tighter latency distribution, statistically, because of how many IOs you're actually reading. And so a lot of people used to use the word max latency. It's just not a very descriptive term. So instead of max latency, it's better to talk about quality of service and tail latency at a certain percentage distribution.
All right, another question we have, and I'll just answer this one. Can we get these slides? Yes, everybody who is signed up for the webinar will get a link to the slides. We'll actually get the slides sent to you. That'll probably be on Thursday. So you'll definitely get slides and a link to the recording. So let me, that question. Okay, next question is, how are the workload characteristics, read-write, random versus sequential block sizes changing for past workloads to drive the need for PCIe Gen 4? I'll start with that one, Matt.
I mean, I'll try to answer it. For us, what we've seen trending-wise on NVMe SSDs is, as John Michael said, there's a lot of database work, and we've seen from the storage side for guys who make their own OSs, et cetera, that they're able to manage the way that they write to the SSDs. So we're seeing a lot of workloads that are sequential in nature, and being able to jump your sequential workloads into double pairs really well, again, when you're pairing it with other CPUs, GPUs, et cetera, that have also increased in their bandwidth as well. We haven't, I mean, that's essentially what it is. I mean, it's an infrastructure upgrade, and you're wanting your Gen 4 SSDs to match the rest of the components in the system. John Michael, if you want to add to that.
Yeah, or I think the way I read the question is, what workloads see the most advantage from Gen 4? So it's really, if you think about PCIe Gen 4, you look at the Gen 3 limitation, and on Gen 3, you say 4 gigabytes per second at the line rate, but at a actual NVMe SSD with the overhead of the command structure, you're seeing about 3.5 gigabytes per second as the max. So any workload that's bigger than that will see a benefit from Gen 4. So sequential read, sequential write, random read are actually probably the 3 biggest, but I mentioned in an actual typical database workload where you're actually increasing the threads on a database read, databases typically read an 8K or 16K chunk size, and a higher QDepth random read of 8K or 16K or even larger, obviously, will give you PCIe Gen 4 bandwidth, and it's higher than Gen 3 bandwidth. So yeah. High performance, kind of workloads, low queued up stuff. Certainly, it's not going to take advantage of Gen 4, but it's going to need to push it a little bit higher.
Very good. Another question: is there any work being done to adopt new emerging technologies such as MRAM, RRAM for better latency and speed? And this one may be a little outside of the scope of this, since those are probably more non-volatile memory questions. But if you guys want to take a shot at those.
No comment here.
Yeah, I'm not sure if let's see. Yeah, Intel has Optane SSDs for low latency and high performance. So yeah, all I can tell you is something really awesome is coming. If you follow Jens Axpo on Twitter, he's got our latest and greatest Gen 4 drives. He's been doing some tweets about it. He's the Linux block kernel maintainer and the creator of IOU Ring. He's doing some real cool stuff with our technology, but I can't talk about that quite yet. It's a little early.
There you go. Okay. Next question. I'm going to try to paraphrase this one. Given we've just introduced Gen 4, when do we estimate that we will actually start seeing Gen 5 SSDs?
Yeah, I mean, let's take an easy stab at it. I think Gen 3 is kind of an anomaly. We ran Gen 3 for 8 to 10 years or whatever. I think between when the spec was released, when the first devices got certified, I actually went to the first Gen 3 Plug Fest. I think it was like 2012 or something like that. That was too long, right? It should be, 2 to 3 year cadence, and PCI 6 back on the cadence where they're actually, being very aggressive for Gen 5, as far as the spec's been released for, now some time. And, yeah, it'll be a couple of years, obviously, from when the spec gets released between when first devices get certified and vendors are on the market. But I'll just say I expect it and anticipate it to be faster than the Gen 3 to Gen 4. That was not typical.
What do you see, Matt? Similar?
I would just say follow the chipset manufacturers. That's the easy way to put it. I mean,
Very good.
as soon as Intel and AMD have Gen 5 chipsets, you'll see SSDs follow.
Very good. Let's hit one more question. We got, in this one we can start out. Probably this is an Intel question. Among various E1S form factor thicknesses, which one should be popular? Which one do you think will be most popular? 5.9, 9.5, 15, or 25 millimeter?
Yeah, this is a tricky one. It's a great question, actually. So I think, we, based on those designs I showed, I think 9.5 and 15 will be very popular. Facebook's definitely gone out and said, they are supporting 25 because in their cloud application, they can get, better airflow. But I think the trade-off on that one is tricky because you really want the increased density of E1.S, the 9.5 and 15. So I think those will be the sweet spot. But good architecture. So hopefully all the SSD vendors will be like us. So, we're trying to basically design one board that supports all three. And by the way, if somebody builds a 25 millimeter slot, it can accept a 9.5 and a 15 millimeter drive. It just, you have to have it put a different latch on there. So all three are mechanically compatible. They all have a 9.5 millimeter rail, and you can just go check out the spec for that. All the mechanicals are in the latest spec on SNIA. But yeah, I mean, I think 9.5 and 15 in the future for Gen 4 and beyond are going to be very popular.
Very good. Now, what do you have any ideas on that one too?
No, I'm gonna defer. I mean, John Michael's answer is right. I mean, Facebook is focused on 25 millimeter. Volumetrically speaking, you're gonna get more density out of a 9.5 or a 15 millimeter E1S thickness. But 25 for cooling, I mean, if you think of, $1 a watt, the more cooling you can get to your drives, the more you're going to reduce the amount of cooling that you need to have on your system.
Very good.
And I guess I forgot
All
to
right,
mention,
and go ahead, Jim.
Oh yeah, sorry. I guess I forgot to mention the 5.9. Where does that leave the 5.9, right? Because Intel has one today. Actually, I think it's a pretty good drive going forward for like small capacity stuff, like kind of M.2 replacement, maybe for boot. But I don't think the data center industry is quite ready to move off M.2 as the standard for boot drives. So it's gonna be a while on that one.
Makes sense. All right, and with that, we're going to wrap up the Q&A. So just as a reminder, we'll be sending out a link to the slides and the recording of this webinar on Thursday. Everybody who's registered will get it. So with that, thank you everybody for attending. Thank you, Matt and John Michael, for being a part of our panel, and I hope everybody has a great day.
Thank you,
Thanks,
everybody.
guys. I only had one Zoom crash that we gracefully recovered for. So
better than yesterday, it sounds like.
Sure. Yeah. Thanks, guys.
Thanks, everybody.
Bye-bye.
Have a good one. Thank you.